In my last video, I introduced a KiCad 8 workflow for generating professional documentation and shared some best practices for schematics and project organization. While that workflow was quite effective, it still required significant manual intervention and was quite prone to errors. Over the past few months, I've worked on automating the entire process, and in this video, I'll be presenting the updated template. First, I would like to thank Setsoft, aka Salvador Tropea, for his amazing work on KiBot, which is the backbone of this template. After contributing many pull requests, bug reports, and feature requests, KiBot has reached a point where it can now automate most of the workflow that I presented in my earlier video. This workflow is designed for seamless integration into a CI/CD environment, which stands for Continuous Integration and Continuous Development. To do so, we will be using GitHub Actions. If you don't have any clue what CI/CD is or how to use it, don't worry too much, I'll be walking you through the entire process. First, we'll have a look at the features of this template and the different files that it can generate. Then I'll explain the general workflow with GitHub and how to set up GitHub Actions. After this, we'll have a look at how to create a project and get started with the template. Then I will walk you through a full example of a project and how this workflow is used across its different stages, from schematic to PCB layout to fabrication. And finally, we'll see how we can run KiBot and use this template locally. So this is if you want to use it outside of a CI/CD environment. For more details and to have a guide in written form, you can refer to the template's README file, which is linked in the description. First, let's dive into an example of what this template can generate. So what you can see here is a web page that is automatically generated by the template. On the left here, you'll find a navigation bar that organizes files into folders for easy access. The web page also supports dark and light modes, so you can simply switch it by pressing on this toggle button here. And the README file that you can see here is directly generated from KiBot. It includes PCB dimensions and images that are also added automatically. You can of course fully customize this file, as I'll demonstrate later in the video. Apart from the README file, KiBot also generates various other outputs. First, let's have a look at the fabrication document. So if I search for the PDF in the navigation bar, it quickly redirects me to the correct file, so let's open it. In the PDF fabrication document, you will see on the left the stackup table, and just below it you will see the impedance table. So this is just to define the different controlled impedances that you need and what are the reference layers and so on. In the middle here, you'll have the fabrication drawing with some mechanical dimensions. And on the right, you'll have the fabrication notes. On the next page, you have the fabrication drawing for the bottom side. Then you'll have a few pages dedicated to the drill information. So this includes the drill table as well as the drill map. And this is done for each drill layer pair. Then we have 2 pages dedicated to the test points. So this includes a PCB drawing with the test points highlighted. On the right here, we also have a test point table with the reference designators and the associated nets for each test point. And at the end of the document, we'll simply have a list of the different layers, and we simply plot the copper layers for each. So almost everything that you've seen in this document has been automatically generated. The only things that still require manual intervention are writing down the dimensions for the fabrication drawing and also providing a template for the fabrication notes, because this is very much project specific. But even for the fabrication notes, a lot of the information here has been automatically generated from the PCB file, such as the board color or the surface finish, as well as all of the dimensions that you see on the bottom here. Let's also have a look at the assembly document. So let me just search for it in the search bar and let's open it. So right away, you will see the top and bottom views of the PCB. And then on the next page, you will have a table for the number of components on both sides of the PCB, as well as the assembly drawing. You can also see that the do not place components are marked with a red cross. And you also have a 3D view of the PCB on the right. We have the assembly notes, of course. And on the next page, we'll have the same thing, but for the bottom side. Similarly to the fabrication document, everything you see here has been automatically generated. So the table with the number of components has been computed from the PCB and the schematic. The assembly drawing, as well as the red crosses for the DNP components, have also been added automatically. And even the images that you see on the right here or on the first page are automatically rendered and have their background removed before being added onto the document. Now let's also have a look at the schematic. So let me just open it. The schematic is very similar to the template that I presented in my earlier video, but many things have been automated. For example, the table of contents on the first page is synchronized with your schematic. The images here for the top and bottom views are also synchronized with your PCB. The dates as well as the version number are all synchronized with an external changelog file and follow semantic versioning guidelines. As was seen in my previous template, at the end of the document you will have the revision history, but in this template, this revision history is also synchronized with the changelog.markdown file. So this is very useful because then you can have everything that is updated together. Apart from the PDF documents that I've shown, KiBot also generates other outputs, and some of the most useful ones are, for example, the interactive bill of materials. Let me just open it. So this shows you the location of components as well as whether you have populated them or whether you have assembled them, and this is very useful during manual assembly. Another useful output is Query, which is a diff viewer to visually track your changes between commits, and this can be done for both the schematic and the PCB file. Finally, maybe the most useful part of this workflow is the ability to compute the board's cost. So this is made possible through KiCost, which is fully integrated into KiBot, and it allows you to compare the prices of your components across different manufacturers, and it will also show you the different specs of your components so you can validate your bill of materials in terms of temperature ratings, automotive ratings, ROHA status, and other specs which can be accessed through the supplier API. Before diving into a full project example, let's first understand the general workflow and how this template is supposed to be used. If you're not yet familiar with Git, I highly recommend learning the basics as it is incredibly useful for any project that needs trackable changes and versioning. For this workflow, I will assume that you know some of the basic Git commands, but I will still be walking you through them in the case that you don't. So now let's break down the standard Git-based workflow at various stages of the project. The workflow is structured around 4 main project phases, which I will also sometimes refer to as variants. Each phase generates different sets of files depending on the project's progress, so here's how it works. The first phase corresponds to the earliest stages of the project when we are still working on the schematic capture and not yet on the PCB. So we will call this phase the draft phase. For the outputs, we'll generate the schematic PDFs, the netlist, as well as the bill of materials. Next comes the preliminary phase, and in this phase, we have the schematic nearly completed, and we've already started working on the PCB. In this phase, we will generate both the schematic and PCB documents, but we will not perform yet the electrical rules check and the design rules check. After this, we will have the checked phase, and at this stage, both the schematic and PCB are mostly finalized. We will generate both the schematic and PCB documents, and we will also perform both ERC and DRC validations. Finally, we will have the release phase, which is identical to the checked phase, but is only for releases. This phase is automatically selected when we push a tag to GitHub and create a release. To manage the project effectively, we'll be using two branches, a dev branch and a main branch. The dev branch serves as the working branch. This is where you'll be pushing all of your changes as you work on your schematic or your PCB. As for the main branch, it is dedicated to releases. Each release marks a stable state of your project when you are ready to deliver files or assets to your client or manufacturer. Releases will be tagged with a version number. Let's have a look at the standard project timeline. We'll be starting the project in the draft phase. This corresponds to the early stages of the schematic capture process, and after making a few changes, we push the changes to GitHub. This will trigger a workflow to generate files like the schematic PDF, the netlist, and the bill of materials. Once the workflow completes, we pull the generated files from the remote repository back into our local repository, and then we continue working. When we move on to PCB design, we switch the project to the preliminary phase. This phase generates additional outputs such as Gerber files and manufacturing documents. As always, we push the changes to the remote repository and pull the updated files back locally after the workflow completes. As the project nears completion, we transition to the checked phase. Here, the GitHub Actions workflow performs additional validations like the ERC or electrical rules check and the DRC or design rules check. At the same time and throughout all project phases, we consistently maintain a changelog.markdown file to document changes following semantic versioning guidelines. Once the project is ready for a release, we open a pull request from the dev branch to the main branch. This formalizes the transition from the development branch to the stable branch. Then we push a tag containing the release version number to the main branch to trigger the release workflow. This release workflow runs KiBot one final time to generate all necessary files, updates the changelog file, and also creates a new release entry on the GitHub page. All subsequent versions or releases will all follow an identical procedure. We'll continue working on the dev branch and push the changes to that branch. When ready, we open a pull request and push a tag to the main branch to create a release. Now that theory is out of the way, let's have a look at how to get started with this template. First, you will need to clone the template under your KiCad's template folder. For Windows, this is in your C drive, then Program Files, KiCad, your version number, then Share, KiCad, and the template folder. Then you can simply clone the repository. So let me just get the link. So just do git clone and the SSH URL of the repository. And now it is cloning. So I will just enter my Git password. And here we go. For Linux, you will need to cd into a different folder. So this is under the user, then share, KiCad, template, and now you should be in the correct folder. So first I will need to give permissions to that folder. So I can just type in the sudo chmod 777 at the root of that folder. And then I can clone the repository. So let me just clone it. And here we go. So now that you have cloned the project, you can have a look at the folders. So if I open it, you will see that in the template folder, we have a new folder, which is the one we just cloned. So it is the KDT hierarchical KiBot folder. Here you will already have a set of files. And the first thing that you will need to do is to install the fonts. So this is optional, but this template already uses a few defined fonts. So you can just go in the KiBot resources folder, then in the fonts, and then you can just install these fonts just like you would any other font. So I would just do right click and install for all users. So I've already installed them, so I won't do it here, but you can do it on your side if you don't already have them. The next thing that you will need are custom colors. This is optional, but I will show you how to do it. First, you can cd into the correct folder. For Windows, it is under the C drive, then users, then your username, then app data, roaming, KiCad, and then the KiCad version number and colors. So let me just open that folder. Here you will see the different themes. So these are JSON files. And if you go in the template, you will see that in the KiBot resources folder, then in the colors folder, I will have defined a theme. So you can just copy this and paste it into that folder. For Linux, the path is slightly different. In this case, you will need to cd into your home folder. Then it is under .config, KiCad, your KiCad version number, and then colors. So let me just open that folder, and you will see that it is identical to Windows. So we simply have the JSON themes here. So you can just copy and paste the file here. Now that you have cloned the template, you can simply create a new project using new project from template. Then you should be able to see the template that you've just cloned. So in this case, it is the hierarchical KiCad design template for CI/CD. So just press OK. And now I can just create a new project. So let me just create a project that I will call KiBot project test. Okay, so this creates a few predefined folders. So let me just open the schematic. Here you will see a table of contents with the board name, the variant, and the revisions, and already a few comments. If you go in the PCB, you will see that there are already a few things that are placed for you. So I will explain in detail what all of these are later in the video. Now that you have created your project from the template, there are still a few things that you might need to modify according to your project. You can go in the KiBot YAML folder and then in the KiBot main.yaml file. If you open it, you will see a lot of stuff, but there are only a few fields that you might need to modify according to your project. So let's go at the bottom of the file, and here you will see different fields. So these are the fields that you can modify. In my case, for the project name, I will simply put KiBot project test. Then for the board name, you can put in the name of your board. In my case, I will just choose a random name like random board. For the company, you can change it to whatever you like. And for the author, I will just put in my name. This logo here is used for the web page. You can change it to any file that you like. For the Git URL, this is also for the web page. In my case, I simply put the GitHub link to this template. Then we have the check zone fields. This option is for filling the zones before outputting the Gerbers. By default, I set it as false, but you can set it to true if you want to refill the zones. The stackup table node is the text that is written below the stackup table in the fabrication document. You can also change it if you want. Then we have two fields for the bill of materials. These are very important, so they need to match the fields that you will be using on your schematic. In my case, I use these two for the schematic, so I will keep these. Then we have three settings for the drill map and drill tables. You can leave it as default. This is what KiCost does, but if your manufacturer asks for different settings, then you could also change these. Then we have the plot refs field. This is whether or not you want to plot the reference designators. By default, I set it as true. After this, we'll have the color theme and the worksheet file. In this case, I just choose the theme that you've already downloaded. And for the worksheet file, this is the block of text that you see at the bottom right of your schematic. I just set it as the custom worksheet that I use for this template. We then have scaling parameters for the document. In my case, I will set it as 1. This you can ignore for now. And another important parameter is the key color. This is the background color that you want to remove from the 3D renders. So the color needs to be different from your PCB. So that's it for this file. And now we will take a look at the workflow file. The next file that we'll have a look at is the workflow file. This can be found in the .github and then in the workflows folder. And if you open that file, you will find a lot of code which defines the different jobs that you want to run in your CI/CD pipeline. This includes, for example, running KiBot in the Docker and generating the files, and also pushing those files back to the repository. The only thing that you will need to change here is the KiBot variant field, and for now it is set as draft, but you will need to change this according to your project progress. If you are just working on the schematic, you can set it as draft. When you start working on the PCB, it will be set as preliminary. And when both the schematic and the PCB are almost finalized, it will be set as checked. When ready for a release, we will push a tag to the main branch, and this will automatically select the released variant and create a release, as I discussed earlier. Another set of files that you might want to modify can be found in the KiBot resources and then in the templates folder. Here you will find txt files, which are actually templates used by KiBot to generate different outputs, such as assembly notes, fabrication notes, an impedance table, and a README file for the repository. So let's open the assembly notes. Here you will find a template that I often use for my project, and you can change these according to your project, or you can just reuse it if you find it useful. Then we can have a look at the fabrication notes file. This is a template that will be used to generate the fabrication notes that you find on your fabrication document. So you can change this according to your project requirements. This is just an example and what I usually use for my projects. The things that start with $, and are followed by brackets will be automatically replaced by your PCB settings or the design rules. For example, the solder mask color might be replaced here by yellow, and the PCB dimensions here might be replaced by the correct dimensions. So this is just an example, as I said, so feel free to change it. Then we have the impedance table file here, which you can use to define the different impedances that you need on your board. So this will be converted to a table in your fabrication document. Here I just put an example for an edge-coupled coded microstrip pair for 100 ohm differential impedance. And here you can define the different layers that it needs to be on, as well as the width of the trace, the gap, and the reference layers. So you can just change it according to your PCB. The last file that you can modify in this folder is the README file. This serves as a template to generate the markdown README file that you will be able to find at the root of your repository. Again, all of the variables that start with $, followed by a bracket, will be replaced by the variables that you set in your KiBot main.yaml file. Here, there's already some code to set side by side some images of your PCB. Then there is a specifications table for your PCB. Here are already set a row for the PCB dimensions. And last, we have the directory structure. So feel free to modify this file according to your project. Now let's create a new GitHub project. For this, you can just click on the plus sign here and then click on New Repository. Then we'll just set the name identical to the project name. In this case, it is KiBot Project Test. You can also add some description. So in my case, I'll just write in test project for the video tutorial using KDT hierarchical template KiBot. You can also set the visibility to whatever you want. In this case, I just set it as public. So let's just create the repository, and now you will see an address that we will use later. Now that you have created your GitHub repository, you will need to enable the GitHub Actions. So let's just go in the settings, and then we can search for Actions, and then we can go in the general options. Normally, it should already be enabled by default, but just to make sure, you can just verify that this setting here is checked. Now that you have your project, you will need to add it locally to your local repository. So let's just copy this GitHub link here. And now we will need to initialize the Git repository locally. Then if we do git status, we will see the different files that can be added. We want to add everything to the repository, so we just do git add dot, which will add every file. Then you can commit your changes. This can be done with git commit -m and then your commit message. In my case, I'll just write initial commit. Now, if we have a look at the different branches with the git branch, you see that we only have a master branch. We want to have a main and a dev branch, so we will need to create the main branch. This can be done with git checkout -b, then main. We can delete the old branch with git branch -d and then master. Then if I try to push my changes, you will see that I still can't push it because I don't have a remote. So we need to add the remote. This is from the GitHub link that you copied earlier. I just do git remote add origin and paste the GitHub link. Now if I do git push, I still can't push it, so I just copy and paste this command here. And now normally it should be pushed to the remote repository on GitHub. So let's have a look after typing in my password. Okay, now let's have a look at GitHub. So normally it should be here, so let's just refresh the page and now you can see your files. Right now we only have a main branch, so we are still missing the dev branch. And it has also triggered a workflow which we can cancel because there is nothing to generate, so I'll just press on cancel workflow for now. Now we still need a dev branch, so we can do the same procedure. We can do git branch and we see that we only have a main branch now. So let's create a dev branch with git checkout -d dev. And then we do the same thing, git push. And we need to copy and paste this command here. So let's just copy and paste it. And now I will type in my password. And after this, normally it should push a new branch to the remote repository. So if I go back into the repository and look at the branches, you will see that I have both the main and the dev branch. Now that you've created a new project, let's have a look at how the template is used in a real example, from schematic to PCB layout to fabrication. Let's start with the schematic. In this simple project, I'll be making a board with an STM32 microcontroller, reading data from a 9-axis inertial measurement unit and powered through a linear regulator. I'll be speeding up the process so you can enjoy this very short time lapse. Alright, so I've finished the first draft of the schematic. It's a very simple hierarchical schematic, and for simplicity I haven't drawn the block diagram yet. So we have here our microcontroller with an I2C bus. This bus is then connected to another sheet here with an IMU or inertial measurement unit. I also broke out the GTAG connection on the microcontroller, and this connection will go to another sheet with the connectors. Here you can see the connector that I'm using for the GTAG, and below it we have another connector which is used to power the system. So it simply goes through a linear regulator and outputs 3.3 volts for the system. Now I will show you how to push your changes to GitHub and how KiBot automatically generates documentation for you. In the project repository, we can type in git status to get a list of the different files that were added or modified. Here you can see that I've deleted the default sheets that come with the template, and I've also added my own sheets. At the bottom, you can see the different files that were added. This includes the sheets and libraries and so on. Before pushing the changes to GitHub, you can set the project phase in the workflow file, which you can find in the .github, workflow, and ci.yaml file. Because we are still in the schematic capture phase, I will set the current phase as draft. This will generate the bill of materials, the netlist, as well as the schematic PDF. If you are using KiCad 9, You can also change the version that GitHub Actions will use by changing the KiCad version field here from 8 to 9. Let's just verify that we are working on the dev branch by typing git branch. And now I can add all of the files by typing in git add dot. We can then commit the files with git commit-m, and you can add your commit message. Now let's just push the changes to GitHub with git push. On GitHub, you can check the different workflows that are running by clicking on the Actions button. If I click on the last one, you can see the different steps that KiBot is currently running to generate the different files. It might take a few minutes, so let's wait for a bit. Now that the workflow has completed, we can check the dev branch, which is the working branch. Here you will see that there are many changes that have been added automatically by the workflow, and these were pushed by the GitHub Actions bot, as you can see on the top. Let's check the images. For now, because we are only working on the schematic, the images will be empty, so this is just a placeholder for the PCB render. Now we can also check the other folders, for example, the manufacturing and assembly folder. In this folder, you will see the bill of materials, which has been generated from the workflow. It is in the CSV and HTML format, and you will see here the different fields that are useful for sourcing your components. There is also another folder, which is the schematic folder, and you will find in it the PDF file of your schematic. Here on the first page, you can see the table of contents, which is automatically synchronized with your schematic. And you also have the block diagram, which I did not complete. And of course, all of the other components and symbols that you've already added on the schematic. For now, the revision history is empty because we still did not fill in the changelog file. The same can be said for the revision number, which is now a plus sign because we are working on the dev branch, which is still unreleased. And you will see later in the video that this will be synchronized with the changelog file. Before continuing to work on your local repository, you should pull the changes that were added by the GitHub Actions workflow. If you don't, you might encounter some conflicts when you pull the changes. To show you how to solve a potential conflict, I will not pull the changes from the GitHub repository and continue working on the schematic. I will be adding a few test points as well as some fiducial markers. Okay, now let's just add the new changes to GitHub. To do that, we can just do git add dot, and then we can commit the changes. So for the commit message, I will just write down what I've done. Here I've added some test points, fiducial markers, as well as mounting holes. So to do that, just do git commit-m and your commit message as usual. Now I will just check that I'm on the dev branch and then push the changes. As I've mentioned before, I didn't pull the changes after the first KiBot run on GitHub, and because I've modified some files locally, it resulted in a conflict. Normally, you should always pull the changes from GitHub back into your local repository before you continue working. You can handle this conflict just like any other Git conflict. In this case, I will just merge the changes. We can have a better look at the conflicting lines by opening Visual Studio Code in the repository folder. In Visual Studio Code, you can see the different changes that are made by the merge commit. So this will just display the things that happen when you merge from the remote repository back into your local repository, and the things that will be pushed to your remote repository. On the left, you can also see the default git commit message. And right now, I will just press on commit to commit the changes. If you happen to see this commit window, and if you've already committed the changes, for example in VS Code, You can simply exit it by pressing Escape and then double column Q and Enter. Now let's push to GitHub the merge commit, which also contains the changes that we've made to the schematic. On GitHub, if you want to have a look at the GitHub Actions run, you can go in the Actions tab and just click on the last run. And this will take a few minutes, just like before, so let's just wait for a bit. When the workflow has completed, we can just go back in the dev branch and look at the different files. So let's have a look at the schematic first. If I go in the schematic folder and then in the PDF, we can see the updated file. And if I go right at the bottom of the file, we will see the different test points as well as the fiducial markers and mounting holes that I've added. Just like before, the last page, which contains the revision history, is still empty. Before continuing to work and before we start working on the layout phase, we will need to pull the updated files. Now that the schematic has been finalized, we can start working on the PCB. Just like before, I will be speeding up the process so you can enjoy this time lapse. So I've finished the initial layout of the PCB. It's a very simple 4-layer board. On the first layer, you can see the microcontroller on the left and the 9-axis IMU on the right. It's connected through the I2C bus. On the other side, we have the connectors as well as the power regulation. So on the left, we have the connector for the JTAG connection, and on the right, we have a connector which is then connected through an LDO and outputs 3.3 volts to the microcontroller. For the two inner layers, I simply filled them with solid ground. You can see that the last layer was named L6, which is a mistake, but this was done intentionally so that we can correct this as we transition to the checked phase. There are also other layers that you should modify according to your board. For example, we have the front and back assembly text layers. On this layer, you can see different elements, and the one you should modify is the group that you see on the right. So this is a group which is called KiBot image, PNG, 3D viewer top, and 3D viewer bottom for the other layer. The size of this group should match the size of your PCB, and this is just a group which defines the dimensions of the image that will be added onto the assembly document. So if you make it bigger, the image that will be added might be bigger than the PCB itself. So I just like to have it the same size, but it's up to you. A few other layers that you might want to modify are the front and back dimensions layers. These define the different dimensions of your PCB, and for the front dimensions layer, we also have some information about the stackup table and the impedance table. The stackup table is computed from your PCB parameters, and the impedance table is computed from the template file which I presented earlier in my video. Then I've also modified the front and back test point list layers. This will define the dimension and location of the test point list tables, and by default the template might have two tables here because this is just to show you an example of Python indexing. We can use Python indexing in the name of the table. So to rename it, just press E, and here if I want to only display the first 5 test points, I might write something like $. And 5, for example. Throughout this template, if you want to change the font that is used in any of the tables, for example, for the test point table or for the stackup table, you can just enter in one of the groups, and then at the top you will see an invisible text box, and you can change the font that is used by this group by changing the font of this invisible text box. Here, for example, I use Arial, but you can also choose any other font. On this layer, I've also added some information about the location of the drill place origin. You can place it by going into the place menu and then drill place file origin. I did it for both of the layers, so on the front and back test point list layers. Before pushing our changes to GitHub, there are still a few files that we will need to modify. First, in the .github folder and in the workflows and ci.yaml file, we can change the project phase. Right now it is draft, but we can set it as either checked or preliminary. I will set it as preliminary for now, as this is still the first draft of the PCB layout. Then we can simply go to our terminal and push the changes as usual. I will just write git status to see what files have been changed, and then I will add the files with git add dot. Then we can just commit the changes with git commit -m and the commit message. In this case, I will write PCB schematic, and this is just the first draft of the PCB, so something like preliminary version. Okay. Then we can just push the changes to GitHub, and I will just type in my password. In a similar way to what we did for the schematic, this will trigger a workflow. However, this one will take a bit longer because there are many more files to generate. Now that the workflow is finished, we can see that the GitHub Actions bot has pushed many different files to the repository. I won't go into too much details for each of the files, as I've already mentioned them in the features section at the beginning of the video. Let's look at the manufacturing document. If I go in the PDF for the assembly document, you will see that I have all of the images at the correct location, as well as the top assembly and bottom assembly drawings. And if I go in the fabrication PDF, we will see that we have the stack-up table, which is computed from the PCB, as well as the impedance table from the template. And we also have the drill map and drill drawings. So this is similar to the features that I've mentioned at the start of the video. We can also see that it has generated an HTML folder. This is for the web page that you saw in the features at the start of the video, and also a Kyrie folder. This is for the diff viewer. On the schematic, we can see that the images have been added and the dates have been updated. We can also see that the variant has been changed from draft to preliminary. Okay, now I will just correct a few things for the checked phase. First, I will rename a layer from L6 to L4. This is simply done in the bot stackup options. So here, this is L4. And because I've just renamed this, I might need to just delete one of the files that have been generated by KiBot. This is manufacturing, fabrication, and in the Gerbers, I can just delete this file for now. I might also want to change a few things on the PCB, but I could, for example, just move this via here as an example. And when we are ready, we can just change the variant name on the YAM file. This is for the GitHub Actions file in the .github, workflow, and ci.yaml file. Here I will change the variant from preliminary to checked. Before pushing the changes to GitHub, you can also change the changelog file, which is synchronized with the revision history on the schematic. If you click here on the schematic, you will see that there are different text boxes, and these contain variables which you can change in the KiBot configuration. So for now, let's open the changelog file. And if we open this, you will see that there is an unreleased section and also some added, changed, and removed titles. Usually I try to follow semantic versioning guidelines, and because this is only the first version, I will just keep the added section. I will just write first version of the PCB and schematic. There is also another file in the KiBot YAML folder which you need to modify, and this is the setText variables file. In this file, we have a section dedicated to the changelog, and this section defines text variables which will be synchronized with the changelog file that you just modified. So if I uncomment this, it will create a new text variables, and when we push a tag to the master branch or the main branch, it will automatically take the information from the changelog file and replace it inside of these text variables. The important thing to note is that the version number that you see here need to match the ones on the schematic. You can set anything really, but it needs to match it. And it also needs to follow semantic versioning guidelines, which means that it is a number dot a number dot a number. The tag that you will be pushing to GitHub to create a release also needs to match these numbers. So when I create the version 1.0.0, I would be pushing a tag containing that version number. Now, as usual, I will just add and commit the changes. So I will just do git commit and write down the commit message as usual. I will call this checked version, and then I will just git push the changes. On GitHub, you will see that a new workflow has been triggered. Now that the workflow has completed, we can check that the changes have been applied. If we go in the PDF of the fabrication document and go right at the bottom, we can see that the layer name has changed from L6 to L4. Let's say that we want to create a release. As I've explained before in the video, we now need to create a pull request from the dev branch to the main branch. So you can go in the pull request tab here and create a new pull request. We want to create a pull request from dev to main. So we'll just select here dev, and for the base it is main. And here you can see the list of commits which will be added to the pull request. And after this, you can just do create pull request. If you are working in a team, there might be someone that needs to approve your pull request before merging. In my case, I am working alone, so I will just click on merge pull request. You can also add a commit message and a description, but I will just confirm the merge. Now, if we go back in the repository on the main branch, we can see that we have a new commit, which is the merge pull request commit. However, we still don't have a release. To create a release, we will need to push a tag to the main branch. To do so, we can switch to the main branch. First, let's check on which branch we are. So right now we are on the dev branch. So we'll just do git checkout main. Now that I'm on the main branch, I need to pull the changes. We'll just do git pull, and this will pull the changes from GitHub. To create a release, we will need to tag the last commit with the version number. This can be done with the git tag and your version number. This version needs to follow semantic versioning guidelines, which means that it's a number dot a number dot a number. Another important point to note is that this version number needs to match the version that you set in the text variables as I've shown earlier. Now we can just push the tag, so this is done with git push origin and the tag name. If you go in your repository actions tab, you will see that pushing a tag has triggered a workflow. In the event column, you can see that we have the tag that we just pushed. And if we go inside, we can see the different jobs that it's running. So we'll have to wait for a bit. Normally, if you check your workflow status, the generate outputs as well as the release workflows should have completed without any errors. Now that the release workflow has been completed, we can go back to the main branch. We can see here that the changelog file has been updated. If we open this file, we see that the old unreleased section has been replaced with the version number and the version date. And there is also a new unreleased section here, which has been automatically generated by the workflow. If you look on the right-hand side, you can see a release with the version number. For the description, this is simply the text that you set in the changelog file. Here at the bottom, we have a list of files, some of which can be sent to the manufacturer, and some others which can be used for documentation. To download a file, we can simply click on it. So let's download the schematic. If I open the schematic, you can see that the variant has been set as released. Here we have the correct version number, and here the date is also synchronized with the changelog. The variant in the title block has also been changed, as well as the git hash. And if you go right at the bottom on the last page in the revision history, you can see that it has now been updated to be synchronized with the changelog file. Now, let's say that I want to work on the next version, for example, version 1.0.1. To do so, I will first need to synchronize my main branch locally with the main branch on the GitHub repository. To do so, I can just do git pull and type in my password. So I am on the main branch, of course. So if I type git branch, you can see that I am on the main branch. Now, to continue working on the dev branch, we will first need to synchronize the changes that we made on the main branch back into the dev branch. To do so, we can first check out the dev branch. So git checkout dev, and then we can pull the changes from the remote back into our dev branch with git pull. I will just type in my password again. And after this, you will need to rebase the changes from main into dev. So git rebase main. Now, if I type in git log, you can see in this git history that our local dev branch is now synchronized with the remote main branch. Here, this is the tag that we pushed on the commit to create a release. And this is the commit that was pushed by the GitHub Actions bot as we created our release. For the new version, as an example, I will simply slightly move the clock trace away. So let me move this for a bit and I will save this. I will then add this change to the changelog. So let's add a new changed section. And here I will just write down what I did. So this is moved the swclk trace away. We also have to update the setText variables YAML file in the KiBot configuration. So because this is quite a minor change, according to semantic versioning guidelines, you can increment either the first, second, or third number. This is a very minor change, so I will simply update the third number here. So this is going to be version 1.0.1. So let me uncomment this. And then on the schematic, in the revision history sheet, we need to make sure to match the version numbers. So here for the body, I have 1.0.1, and for the title, I also have 1.0.1. Of course, you can move these here if you wanted to. I will just leave it here for now. Now we can commit the changes to the dev branch on GitHub. To do so, we just do git add dot, then git commit -m and the commit message. In this case, it will be moved the swclk trace, and then we can simply push the changes. As usual, if we go in the Actions tab, we can see that a workflow has started, so we can wait for a bit for it to complete. To create a new release, we do just like last time. So we will create a new pull request from the dev branch to the main branch. Then we just set the title. I will just write new version 1.0.1, and for the description, move the swclk trace. Okay, now I'll just create a new pull request. And now we can simply merge the pull request. So confirm merge. And now on the main branch, you should have the last changes. Just like before, we now check out the main branch. Then we pull the changes. After this, we will need to tag the commit. So I just do git tag 1.0.1. So this is the same number as the one that we set for the pull request. And then git push origin 1.0.1. Once the workflow has completed, it will create a new release entry here, as well as update the changelog. So if we go in the changelog file, you can see that we have a new entry here and a new unreleased section. Now let's just download the schematic just like before. So I will go in the assets and download the PDF. And you can see here that just like before, the revision number, as well as the dates and the revision history have been updated. In this section, I'll be showing you how to run KiBot locally. The easiest way to install KiBot locally is with Docker. To install Docker on your platform, you can simply follow the instructions on the official website, which I will also put in the description. Now that you've installed Docker, the first thing that you will need to do is to run Docker Desktop. You can simply launch the Docker Desktop application, and once it has been launched, you can just close it. Under Windows, a small icon appears at the bottom or in your icon trail when Docker Desktop is running. To run KiBot in a Docker, you can go in your KiBot resources directory and then in the scripts folder. Here you will see multiple files, and depending on your platform, you will need to run one of these executables. My left terminal here is under Windows, so I will be running the docker KiBot windows.bat. To run the script, you can simply write down // and then docker KiBot windows.bat. You can also add a flag to specify the KiCad version, which is the V flag. If we want to run with KiCad 9, we will be writing down -v and then 9. And by default, it will be using version 8. So right now, I'll be just using KiCad version 8. So it will try to pull the image from Docker Hub, and once it's finished, it will automatically enter the Docker container. Under Linux, the process is very similar. First, we will need to cd into the KiBot resources folder, and then in the scripts directory. Here there are also multiple files, and because we are under Linux, we will need to run the docker KiBot Linux bash script. But before this, we will need to give the proper permissions. You can do this with sudo chmod +x and then docker KiBot linux.sh. So we'll just type in my password. And now you should be able to run the script. So just do / and then docker KiBot linux.sh. Just as an example, I will be running KiCad version 9. Before continuing to work, you will need to cd back into your project folder from the Docker container. Normally, the Docker container should have access to the local files from your host computer. Here under Linux, I can simply cd back into the project by doing cd KiBot project test, but you will need to check where it is saved. And under Windows, I will simply cd back into my documents and then GitHub and then KiBot project test. Once you are inside of your project repository, you will see that there is a KiBot launch.bash script file. This is a helper file to help you get started with KiBot locally. To have a look at how this is used, you can simply launch KiBot launch.sh with the help flag. Here you will see how this is used, and the command that you will be using most often is this one. But you can also pass a variant, as we saw before. So for example, the released variant or the checked variant, by default, it should be using the checked variant. It can also be used to compute costs, and this is for generating an Excel spreadsheet, which I will show you later in this video. And it can also be used to run a web server, and this is the web page that you saw at the start of this video. Okay, so now let's just run the standard KiBot launch command. So I will just type in KiBot launch.sh, and you will see here the different commands that it will be running. After the workflow completes, we can see that the generated files are identical to the ones that are generated in our CI/CD environment on GitHub. Just as a warning, you shouldn't try to use KiBot in a CI/CD environment and locally at the same time if you are using the same variants for both. This is because these will affect the same files and could result in merge conflicts. If you are using assembly variants, which I will show you later in this video, then this is fine because assembly variants are saved in another folder. We will now have a look at how to compute the costs of your bill of materials. This is done with KiCost, which is fully integrated into KiBot. KiCost uses the supplier's API like Mouser or DigiKey to generate a spreadsheet which not only contains the cost of each component, but also other information such as voltage ratings, ROHS status, temperature ratings, and so on. In order to access the supplier's API, you will need to provide the API key to the correct file, and this can be done by going first in the KiBot YAML folder, and at the bottom you will find the KiCost config local template file. So you can just copy and paste this file and rename it to KiCost config local.yaml. Normally, you will see that this file is grayed out. This is because it is inside of your git ignore. This is because we don't want to share the keys to GitHub. So now all that is left to do is to fill in the keys and the other information that you need. Each supplier will have a specific way to get the API keys, so you can just look it up by typing in the supplier name followed by API. Once you've set up the YAML file with the different supplier keys that you need, you can just go in your root folder for the project and you can launch the KiBot launch.sh script with the cost flag. So this will launch the command to generate the Excel file with the different costs. Right now I only have Mouser because I have some issues with my DigiKey API, but you can try to add some other suppliers if you need. You can then find the file in the manufacturing and assembly folders. So here we have the XLSX file, and if you open it, you can see that we have a file with different tabs. The first tab is the bill of materials, where you have a list of your different parts. Here you can see in red that I have not completed these fields, so this just flags an error. So this is something to fix later on. And in the cost tab, you can see how the cost is computed. Here you can also see some red rows. So this is also warning because here I have no stock available for this part according to the supplier API. And here we have a color tab. You might have another tab with other fields, but this really depends on what API you are using. On the right side, you will find some statistics for each of your suppliers. So for example, here for Mouser, I only have 14 out of 19 parts that have been found. And some of the other parts are either out of stock or obsolete or so on. So this is very useful in order to check your bill of materials. On the bottom, you will also see here a buy here button, and this will automatically create a basket on Mouser so that you can buy directly the components. So this is also very useful. Now, if you want to generate the website, which will allow you to navigate the different files generated by KiBot, as I've shown at the start of the video, you can simply launch the KiBot launch.sh script with the server flag. So here you will see some text and you can just open this URL. And if you open this URL, you will see here the website. As I've shown at the start of the video, this will generate the web page that you can see here. And we will have here the README file, and we can also look for different files, for example, the assembly document, so PDF assembly. And this is just an example of what is generated by the workflow. So this is very useful if you want to navigate very intuitively through the different files of your project. So this is it for this video. I hope you liked it and that you found it useful for your own projects. It took a bit more time than expected to put this together, as I wanted to use it in personal and professional projects before I actually release it. I still didn't fully explore the different capabilities of this template, and especially for the variants, like the different assembly variants that you can generate. So let me know if you want another video concerning this topic. I will keep making advanced KiCad tutorials, and one of the subjects that I will explore is the use of database libraries to really have professional library management in KiCad and how I use it in my projects. So stay tuned for that, and see you next time.